Hi everyone, we're going to be talking about section 1.7 today, and I'm sorry I'm not there with you in person, but I know we can do this. So we're going to talk about inverse relations, and first and foremost, let's talk about what an inverse relation is. An inverse relation is when for every coordinate point A, B, you have a corresponding coordinate point BA. So what does that mean? If you have two relations, for every coordinate point A comma B, the inverse has B comma A. All right? So basically all of the X values become Y values and all of the Y values become X values. All right, here we have a couple of different examples of, here we have a couple of different representations of two inverse relations. So we have y equals x squared minus 4. And when we graph y equals x squared minus 4, we get this parabola that intersects at y equals negative 4. Now, here we have the coordinate points for this parabola. When x is 0, y is negative 4. When x is negative 3, y is equal to 5, and so on. Now, when we take this relation and when we switch all of the x and y values, so look here, x is negative 3, y is negative 5, becomes x is 5, y is negative 3, right? They switch. So if we take a look at this one, 1 comma negative 3 switches to negative 3 comma 1. And when we graph that relation, we have this in the green, right? So the blue and the green are inverses of each other because what did we do? For each coordinate point, we switched x and y values. Okay? Now, what's one thing that we notice is if I draw another line, y equals x, then the one parabola is reflected in the line y equals x and it makes the other parabola. Now, if we find the inverse of a function and the inverse also happens to be a function, then we denote it by f inverse of x. All right? So not all functions are going to have inverses which are functions. Take a look at this parabola. The parabola in the blue is an amazingly cute function, but its inverse in the green is clearly not a function, all right? Because it doesn't pass the vertical line test. So now, could we have known that from the beginning? Well, yes. So if you see here, the blue parabola, when we find the inverse, is basically inverted on its side and becomes that horizontal parabola, right? So from the beginning, if we test for functions using the vertical line test, then we can do a horizontal line test, and that will tell us from the beginning if the original function will have an inverse which is also a function, right? So the horizontal line test says if you draw a series of horizontal lines through a function, and if the horizontal lines only pass the graph one time, then its inverse will be a function. All right, so let's take a look at some of these. We're going to graph each of these using a graphing calculator, and with the horizontal line test, we're going to see whether or not they have inverse functions. All right, so take a look at this one. We graph 4x squared plus 4x plus 1, and clearly we get a parabola here, and it doesn't pass the horizontal line test, so no, it does not have an inverse function. Now, when I graph the second function, x to the 5 plus x cubed minus 1, you see that, yes, it does pass the horizontal line test, so its inverse will be a function. All right, now, here's another another piece of terminology that we need to be introduced to. If a function passes the horizontal line test, then we say it's 1-to-1, because no x value is matched with more than one y value, and no y value is matched with more than one x value. So basically, for each x value, there is only one y value, and for each y value, there is only one x value, right? So if you take a look at this one, For one y value, you have two x values. So this is not 1 to 1. Okay? But something like this function where for each x you have one y, for one y you have one x, that is 1 to 1. All right. Now, if a function is 1 to 1, then what happens when you find the inverse of a function? Basically, because we said in the very beginning that we're taking each coordinate point, a comma b, and changing it to b comma a, then if these represented the domain and these represented the range, then what happens in the inverse is the domain of f of x becomes the range of f inverse of x. So if I have f of x, and if I have f inverse of x, and I have the domain and range, what will happen is the range will become the domain of f inverse, and the domain will become the range of f inverse. So they swap. Okay. Finally, how do we find an inverse function? Well, we've been saying this, switch x and y, switch domain to range, and so on, and that's where it comes from. So first and foremost, figure out whether the function has an inverse, right? Using the horizontal line test. Now, once you've determined that it does have a function, replace f of x with y, and then interchange x and y. Solve for y, but then we have to call it f inverse of x in the new equation, and then we have to state any restrictions. Okay, so let's go ahead and do this first one. So this is x over 2x minus 1, and you graph it and you see that it does in fact have an inverse function because it passes the horizontal line test. So we're going to rewrite f of x as y. Right? Nothing new here. No math is done in the first step. Then we're going to interchange x and y. So this is going to be x equals y over 2y minus 1. All right. Now I need to solve this for y. I'm going to cross multiply. So x times 2y minus 1 is equal to y. Distribute 2xy minus x is equal to y. Okay, we're going to go over here. Now what I'm going to do is I'm going to add x to both sides. So that's going to be 2xy equals y plus x. Subtract y. 2xy minus y equals x. Remember, I'm still solving for y. Factor out a y, 2x minus 1 equals x. Divide by 2x minus 1. Y is x over 2x minus 1. Okay, that's the inverse. All right, so what am I going to do though? I can't leave it as y because this is the inverse. I have to write it as f inverse of x is equal to x over 2x minus 1. Remember, Precalc Honors is all about notation, right? If this is f inverse, you have to say that it's f inverse. Okay, let's just think about this for a minute. What just happened? I had f of x, x over 2x minus 1, and now I have f inverse. It's the same thing. Wait, can that happen? Well, let's take a look. So here is x over 2x minus 1, right? Now, let's also put in here y equals x, because if I have an inverse, it is reflected around the line y equals x. The function is reflected around the line y equals x. So if I do this, and now if I take this screen and if I fold it around this red line y equals x, do you see how the function becomes its own inverse? It maps onto itself, right? And so it's very possible that it is its own inverse. All right. And as far as restrictions, look at the denominator. 2x minus 1 cannot equal 0. 2x cannot equal 1. X cannot equal 1 over 2. So that is my restriction. All right, let's move on to this next one. I'm going to say y equals 2 root x minus 1. First, I think to myself, does this even have an inverse function? Well, the square root graph does pass the horizontal line test, so yes, it does. All right, let's replace x with y. All right, now I'm going to solve for y. Divide by 2, divide by 2. X over 2 is equal to the square root of y minus 1. Take the square root of both sides. X squared over 4 is equal to y minus 1. So y, when I add 1, x squared over 4 is equal to, x squared over 4 plus 1 is equal to y. Okay, so now I have f inverse of x is equal to x squared over 4 plus 1. But now I have an issue. My issue is f of x was a square root. Now f inverse is a parabola. Well, I can't have that. All right, so let's see what I mean by that. So if I have 2 times the square root x minus 1 that's what that looks like. So if I have this, that's 1/2 of a parabola. All right. Now, when I graph x squared over 4 plus 1, I think I'm going to get rid of this. X squared over 4 is 0.25 x squared. Plus 1. All right, look at what that looks like. So the first arm of this is my inverse. Everything to the left of y equals 0, or I'm sorry, everything to the left of x equals 0 is extra, right? So how am I going to restrict my domain? I say the domain is negative infinity to 0, which means I am telling everybody, please just take the right of this. Everything starting from 0 to infinity. That is the inverse of the half of this parabola, right? One arm of this is equal to one arm of this. So that is my inverse and my restriction. All right, take a look here. Here we have m of x is x squared. Okay, well, what does that look like? X squared. But I already have an implied domain here. I already have a restricted domain. It says just take everything which has an x value of 0 to infinity. So just this, right? So with the restriction, it's the parabola, but only from x equals 0 to infinity. Now, does this pass the horizontal line test? Yes, it does. So y equals x squared. Switch x and y. Take a square root. Take a square root. Now I have y is equal to plus or minus the square root of x. So can I take both of these? Let's see what they look like. If I have the square root of x, it looks like that. Negative square root of x looks like that. All right. Can both of these be the inverse of that purple? No, only one can. So I have to get rid of this. Only that, the top part, is the inverse of that purple. So I have to say just positive root x. So now I have f inverse of x is positive root x. Now, what's the domain of root x? 0 to infinity. I can leave it alone. I don't have to restrict it any further. Just root x is good enough to be the inverse of m of x. So that's that one. Oh, notation issue. That's not f inverse. That's the inverse of m. So it has to be m inverse of x. Okay, moving on. Compositions of inverse functions. All right, so here's a theorem here. It says two functions are inverse functions if and only if f of g of x is x, g of f of x is x. So now, it says here show algebraically. It should actually say verify. When you hear the word verify, there is only one way to verify that f and g are inverses, and it is using this theorem. And so what you have to do is this. You have to split your page into two. In the first hand, you have to find f of g of x. And then on the second hand, you have to find g of f of x. All right, so let's do that here. F of g of x. So this g of x goes into f of x. So that's going to be the square root of g of x minus 8 plus 5. This is going to be the square root of x squared minus 10x plus 25 plus 5. Let's factor x minus 5 squared plus 5. Okay, squared and square root will cancel each other out. So I have x minus 5 plus 5. So finally I have f of g of x is equal to just x. Okay, all right, so far we're on the right track. Now let's do g of f of x. It can't work for both, or can it? All right, so x squared. So g, x minus 8 plus 5 squared minus 10 times g plus 33. Right? Is that right? X squared minus 10x plus 33. Yes. Okay. So let's see. This is going to equal. All right. If I square this one, the first term squared is x minus 8 plus 2 times 5 is 10 root x minus 8 plus 5 squared is 25. Now I distribute the minus 10 root x minus 8 minus 50 plus 33. Okay. Positive 10 root x minus 8, negative 10 root x minus 8 go away. So I have x minus 8 plus 25 minus 50 plus 33. All right. So 25 plus 33, 58. Minus 8 is 50. So all of that goes away. So now I have g of f of x is equal to x. All right. So look at what I have. F of g of x is x. G of f of x is x. So yes, f and g are inverses. Now, you have to be very, very careful here. You have to do both of these. You have to get x for both of these. It's an all or nothing deal. If you do f of g of x and g of f of x, and let's say you get 0 for the first one and you get 0 for the second one, no, that doesn't work. You have to get x for both of them. That's it. Now, if it fails from the first try here, let's say it failed here, then you can just stop. You don't have to go further because it's an all or nothing deal. Okay. All right, here, use the graph of each function to graph its inverse. So this is pretty straightforward. We're going to take each coordinate point and switch x and y's. So here's one coordinate point. That's x is negative 3, y is 0. right? I just take a couple of like representative ones, and if I can take the ones on the corners, I take the ones on the corners. So this is -2 comma -1, and then I have another one here, 1 comma -2, and then I have another one here, 6 comma -3. So all these now have to get inverted. So I get 0 comma -3, -1 comma -2, -2 comma 1, -3 comma 6, and I just graph those. So x is 0, y is -3, x is -1, y is -2, x is -2, y is +1, x is -3, y is 6, right? And I just connect those, make it look like the inverse, and there you have it, right? Now, is that really the inverse? Well, let's see. Let's graph the line y equals x. Is one a reflection of the other around y equals x? It is. If I fold this paper along the red line, the original and the green will overlap. Okay, so that's one there. Let's do one that's a little bit more involved. Ooh, look at this one, right? So this one looks like there is an asymptote here. Okay, so let's do it. Let's take some points. Okay, so I'm going to take, let's say, this point, right? That's x is 1, y is 0. And then what else am I going to do? I'm going to take this point, right? Okay, so where is that point? That's not even on a corner. Well, let's see. My x coordinate there is somewhere between 2 and 3. And my y coordinate is 1. Okay, you know what? Let's see what we have here. When this gets inverted, I have 0 comma 1. So when x is 0, y is 1. Here, my x value is going to be 1, and then the y value is going to be somewhere between 2 and 3. So my x is 1, and my y value is somewhere between 2 and 3. All right, so let's see what else I have here. It looks like here I have an asymptote, a vertical asymptote at x equals 0. Well, now that we're switching domain and range, the vertical asymptote becomes a horizontal asymptote right here. And if it's in the negatives, it will stay in the negatives in the x values. Okay? Now, it looks like there might sort of be like this flattening out around, you know, x equals 2. So we're gonna sort of flatten it out around y equals 2 right here. So what is my inverse going to look like? There, right? So any phenomenon that happens along the x's now repeats but along the y's, and vice versa. Okay? And again, if you draw the line y equals x, you see that clearly one is mirrored into the other. All right, so that's that. Please complete this for next class, and I will see you next class. Bye, guys.